I hope everyone is well. We're going to start our exploration into Chapter 6 today. And one of the fundamental parts about Chapter 6 is understanding what carbocations are. Carbocation. What is a carbocation? Good question. Carbocation is a species where carbon has a positive charge. This is not normal for carbon. How many bonds does carbon have if it's going to have a positive charge? It's going to have 3 bonds. So that answers what is a carbocation. These can be carbon groups or hydrogens. So we could have a methyl carbocation, where those are all hydrogens. Oops. Okay. All having the Monday yips here. Here we go. Methyl carbocation, a primary carbocation. Let's try to do this so I don't have to keep doing the same thing over and over again. Good. We're going to have a secondary carbocation here. And yes, you guessed it, we'll have a tertiary carbocation over here. So some kind of carbon group here and a hydrogen and a hydrogen. And over here, I don't know. What are we going to show? Just carbon's fine. Here we got a couple carbons and a hydrogen. And here we have all carbons. So those are our carbocations for the next couple weeks. Methyl is the least stable. Why are all of these so unstable? That's the second question in the sentence at the top. And of these there's 4 of these. This is the most stable, the tertiary. Primary means 1 carbon attached to the carbocation. Secondary means 2 carbons attached to the carbocation. Tertiary means 3 carbons attached to the carbocation. Methyl, 0 carbons attached, nothing but H's. Why are they so unstable? Well, 2 reasons. The main reason, carbon is not stable unless it has a full octet, and carbocations, because there's only 6 electrons around each of these carbons, has an octet violation. That's the number 1 reason, and it's the most important by a long shot. That doesn't look like a number 1, does it? And then a distant second, we have a charge, formal charge, charge, this typo, formal charge is more stable, less stable, sorry, than neutral. Stable than neutral. We've been seeing nothing but neutral carbons until now. And why is a second? What do they do? Oh, okay. What do they do? Here's what they do. What do they do? They react with nucleophiles. Nucleophiles. That's what they do. Remember, nucleophiles love the nucleus. They have to have a lone pair to do so. And when all of these are finished reacting, they will not have a charge and they will not have an octet violation. Those curved arrows mean lone pairs making a bond to the carbon. Carbon will be back up to 4 bonds and carbon's charge will be 0. So that's what they do. Okay, I take it back. That's one thing they do. Later on, we'll see that there's other options of getting a full octet. In later chapters, we'll see how you can make a pi bond to a carbocation. But we're not ready for that. Why is a secondary carbocation more stable than a primary carbocation? That's a very good question. And then a tertiary cation is even more stable. I think we need a new page for that last part. I hope you've noticed that all of these are sp2. C plus is sp2. How did we do that? Same way we did it on our first test. sp2, we have 3 sigma bonds, and 0 lone pairs. Count those things up, you got 3. sp2 hybrids are used to make the sigma bonds. Empty p orbitals where the plus lives. So trigonal planar, plus in empty p orbital. On our next page, we'll draw that out. Right now, let's get a little box around this of some kind. So, next page. You got your C. Now, if I take the plane of that cation from this page, they're all flat on the plane of the page. So they're all like this up against the page. And I'm going to rotate that 90 degrees. And let's see what we have. The bond straight to the left, still straight to the left. The bond that used to be here is rotated 90, so it's going to be sticking out of the page. And the one that was up here is going to be behind the page. And that way I can show this empty p orbital. P. And these are all hybrids. Green equals hybrids used to make bonds. Okay, so we got this lovely carbocation here. Plus is in a p orbital. We'll just put them all here. It made a bold statement about the tertiary being the most stable and the primary being the least of these 3. So let's look at primary here. 1 C, 2 H's. Secondary here. 2 C's, 1 H. Tertiary here. 3 C's. I hope we can agree that the least stable part of this thing is the cation, and it needs stabilizing. Well, the only thing that can stabilize a cation is electrons near the cation. When you have a hydrogen bonded here, there are no electrons up here, and there are no electrons down here. There's nothing near this p orbital with hydrogen here. But with a carbon there, with a carbon, the carbon has bonds. And guess what is in a bond? You guessed it, a pair of electrons. So that's a sigma bond, sigma off of an adjacent C carbon. And that pair of electrons, if it's sticking up in this direction, has the right orientation, that's in the plane of the page here, to get close to this orbital. That causes the orbital to become more stable. And I'm going to show the interaction with this yellow. That just says the electrons are close to the empty p orbital. Okay. You can't say the same for these electrons or these electrons, but you can for these two electrons here. Why? Well, this is on a dash, which means it's going behind the page. It has a different orientation than the p orbital. The wedge is coming out of the page. It's in this area out here where there's no p orbital. But this one in the y-axis is of the right orientation to stabilize that. So on the other ones, we have a similar thing. I mean, we could rotate this carbon so as the H there. It doesn't have to be an H either. It can be any bond. Let's go back to our normal bonds here. Could be that bond, in which case this one's not helping and this one's not helping, but this one is. And we'll show the helping with that yellow again. It's just, these are just saying the electrons are close enough to help stabilize the other half of the p orbital if it's pointing down. And we got the same story up here. I keep having to adjust my pen width. It's worth the wait though. That does not have to be an H. Any bond. Same good interaction. We better give that good interaction a name or else we'll just have to keep saying the electrons in a sigma bond off of an adjacent carbon have the right orientation sometimes to stabilize the p orbital. We need words for that. So the words for these symbols, one big fat word, hyperconjugation. And here we have times 1, primary, hyperconjugation times 1. Over here, times 2. I got both of them showing up there. And in our last one, it'll be times 3. Guess which one's the best story? We got a bond down here. We got a bond up here. We got a bond down here. My molecules are running into each other. Can I just kind of move this H in a little bit? Not changing anything. I just need the space. Now you're going to think the H is important because it's so big. Okay. So I got this bond here with electrons in it. And yeah, hyperconjugation times 3 is the best. So that answers the question. What was the question? Why is a secondary carbocation more stable than a primary? And your answer, if you had to put that on a test, would be the secondary carbocation has twice as much hyperconjugation as the primary. Pictures show it. Twice the hyperconjugation as the primary. Tertiary is better than secondary. It has 3 versions of hyperconjugation. Here, I don't want you to think these two are touching each other. There you go. It has this one, and this one. So that is why it is much easier to make a tertiary carbocation than a secondary. And similarly, it's easier to make a secondary carbocation than a primary. So remember that when we start our mechanisms very soon, like in 10 seconds. Now we have in our book, we have mechanisms starting in chapter 6.1a. Reaction of alkenes with HX, typically HBr or HCl. Not exclusively. HI is often used. HF is not going to work. It's not a strong enough acid. Another way to say this would be what happens to the molecule. You add a hydrogen and you add a halogen. And we're going to start with a very simple example. Get our pen back to its normal thickness here. Here's the overall reaction. We'll react it with HCl. And you're going to get a mixture of 2 products. Oops, I got an octet violation to start with. There, fix that. You get 2 products. Both have the same skeleton. And one of the products, the Cl, goes in the middle carbon. And you get the H part of HCl there. And the minor product, for reasons we have almost already discussed, we get major and minor. It has to do with carbocations. The secondary carbocation will become this product. And it's easier to make a secondary carbocation than the product that this came from, which was a primary carbocation. And the mechanism starts like this. Saying, wait, why am I not putting this in my journal? Well, you hold on the journal. I'm going to tell you exactly what goes in your journal. And I haven't told you yet, so don't put it in there. These 2 species react first. And this is a slow step. When studying reactions that have multiple steps, the slow one is the most important one. We call it the rate determining step. It's the one that holds the reaction rate down. One second. No. I think I can go like this, though. We're going to make 2 carbocations. First one was if you put the H over here, then the middle carbon is missing an octet. That's a secondary carbocation. And the second one, if I put the H on the middle carbon, then I get that primary carbocation. And the mechanism goes like this. The mechanism is, how do the valence electrons move to create this new sigma bond? or this new sigma bond and the carbocation. And here's how you read these arrows. First arrow starts on the pi electrons of the alkene, attacks the very positive hydrogen atom. Why is it very positive? Well, you would be positive too if your electronegativity was 2.1 and you were bonded to something with an electronegativity of 3.0. It's not necessary to put the charges here, but it's reminding us why this atom gets attacked and not this one. Now, if you do just this one arrow, you're going to make a sigma bond to H, and the H already has a sigma bond to Cl. You would have an octet violation on hydrogen, and you're never allowed to have extra electrons on hydrogen. So you compensate by using this arrow, and I'll tell you what that arrow is. The sigma bond is breaking between H and Cl and becoming a lone pair on chlorine. That means you made chloride. And you say, wait, why is he putting the lone pair on there? Chloride has 4 lone pairs, or else it's not chloride. The reason I'm showing that lone pair is it wasn't there before. We like to show lone pairs that are new, or we like to show lone pairs that we need for another part of the mechanism. You do not have to draw lone pairs ever unless they fit in one of those 2 categories. They're new, or they're going to be used in another part of the mechanism. In this case, it's both. So when you made this carbocation, you also made a chloride. And when you made this carbocation, you also made a chloride. And I have a lot of students out there, have a physical chemistry bent to them. And they're saying, that equation's not balanced. You can't do that. To you, I have this discussion right now. Hypothetically, let's just say we started with 100 molecules. Approximately 75 of them became this, and the other 25 became this. So yes, I still have 100 molecules that came from 100 molecules. 75, 25. When I made these 75, I reacted 100 molecules of HCl here. I made 75 chlorides this way and 75 chlorides this way. All atoms accounted for. This is balanced perfectly well. There you have it. That's the slow step. Yeah, why is it slow? You should be able to tell me why this would be very slow. Generally, reactions that make unstable molecules are slow. That's a potential energy argument. We have reactants becoming products. Oh, it's backwards on the screen, so I assume it's backwards on your screen. Oh, I can't do my hands when I'm thinking backwards. It's endothermic, which is usually slow because in an endothermic reaction, there's a very high barrier. Activation energy, we call it. And it's endothermic because having an octet violation is less stable than having full octets. Having a charge is also less stable than having no charge here or here. The fast step, we're going to take this thing here. I don't know. Can I get the whole thing? It looks like I can. Oh. Both of these would be very fast. Wonder if I'll be so lucky down here. I don't need the label here. There. These are going to both be very fast. The chloride you made, what's going to happen is the lone pair is going to be used to make a sigma bond to the carbon that's a carbocation. The lone pair, okay. The lone pair is going to be used to make a sigma bond to the carbon that is a carbocation carbon. And this will give the 2 products illustrated at the top of the screen. CH3, CH, CH2, CH3, CH, CH2, bottom one, put a new H on here in the slow step and a Cl on the end, and this one put an H here on the slow step and a Cl here at the end in the fast step. Why are these fast? We got rid of 2 charges. That would always be fast. We got rid of an octet violation. Isn't that the even more important reason? Yeah. They'll be very exothermic, these steps, because you took something unstable and made it more stable. And you got rid of both octet violations, that's the most important thing, and charges. And I don't want to see this in your journal at all. There's way too much writing here. We had all the stuff that was already on the screen from before. I'm going to make this into a journal entry right now. I'm not going to copy what I have, though. I think, let's see what we get. I can live with that. Copy this into your journal. I'm going to write that down. Uh, 8.5 by 11-inch paper. Handwritten. Handwritten with an N. Nice. Okay. Seems important. And you're going to submit your journal on test day. And it'll have stuff you were told to copy from class. So everything you see here, you're going to copy. The mechanism. If this was a test question, this part would already be on the test. Everything you see here. You would have to provide the arrows and the intermediates. So you don't have to copy the reaction out. The teacher already has it there. Although, COVID semester, we got to copy it out first. So you don't get to save that step, but you'd start right here. That is that first slow step that we did right here. Didn't need to copy it out there. Start right up here if you want. I'm going to go straight to stick figures too. That'll save a lot of time. And you're going to go here. You don't have to write words either. So journals can be in red and green. The stuff you got to put there. Blue. You're going to make this cation and a chloride. And you're also going to make this cation on the end and a chloride. That was a lot easier than drawing CH3, CH3. That would be a CH3 now, wouldn't it? And I said, oh, wait, I don't see the new H on there. But there's a new H on there. Is there a charge on here? No. There's got to be 3 H's. There was only 2 before. Where's the third H come from? Right here. Hey, how do you know this is a CH2 now? Oh, I don't see any charges, and it's a stick figure, so it has to have 4 bonds. 2 are missing, 2 H's. There was only 1 H before. Now it's got 2. So that's this H right here. There's a cation. It's going to be a chloride on there next. And last step, don't redraw anything, please. Draw your intermediates one time. Draw your intermediates one time. And watch out for those arrows. I will say this very slowly. You want to lose a point or a half point? Let's do stuff that I don't like to see. Just so you know, I don't want to see it. I'll have students that say, you just make a bond to the carbocation. They use those words. They take it very literally. They take themselves too literally and they go like this and they say, yeah. Nope. No, I don't know how to make it clear enough. Don't be putting that on your tests. Bond, this is below your mechanism. Mechanism's over. Sorry, I got carried away. It's just ignoring me. End journal. Wow. End journal entry. Everything after that is notes. So you're saying, I don't see the difference between this and this. Well, I'll tell you the difference. The bond is to carbon, not to a plus. Remember, a plus is just a charge. It's not even a thing. It's describing the carbon's charge. Bonds are to atoms. Please tell me which atom. See, that arrow ends right at the carbon. This arrow ends right at the carbon. If you have it ending at the charge, you're going to lose a half point. Not a full point. You've got the general idea, but you're just not accurate enough on your arrow. I don't want to see anybody losing a half point. Notice my arrows always end at atoms or at an atom here. Sometimes they become a sigma bond. There's a sigma bond to this carbon that wasn't there before. Sometimes they become a lone pair. There's the lone pair right there. Okay, so that's a complete journal entry. You need a section number and a title. You can copy them from the textbook. I know these might not be the exact words for 6.1a, so you can use the exact words for 6.1a, copy it so it helps you study, and then do the mechanism that I tell you to do right here. And we can do another journal entry together, and this one will look more like it started on a test. I'm going to steal it from ChemDraw, and that was a rather long introduction, though. We're going to pick up after the break. I'll show you what it's going to look like. You can do a, let's do this. So if you want to quickly copy that down and try the mechanism on your own and figure out which one's major and minor, that's where we're going to be starting after the break. So you can do a screenshot, whatever. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And I'll see you after the break.